Okay, good morning, you all. I hope you are all doing fine. Before we start, do you have questions, guys, about the types of proofs we have gone through on Tuesday? The direct one and the indirect proofs, do you remember them? Proof by contradiction, proof by contraposition, proof by induction, and lastly, recursive proofs. Do you have any questions regarding these, or are you comfortable with all the types of proofs? No questions? Then okay, we can quickly do a kind of review of the previous slides and then finish this chapter today. Maybe if you have time, I can start the next chapter, which is on data structures, the main data structures we usually use in Python programming language and some other ones, so that you have some basic knowledge about the data structures, and in your implementations, in your mini project, it will be easier for you to write some specific algorithms. I will quickly go through. This is another reminder. The first part of the mini project, make sure that you finish a kind of a tutorial and prove it by taking a screenshot or just uploading a kind of a certificate if you have. And the assignment is already available on multi-class. You can simply upload your documents. We discussed the terminology of proof. We discussed theorem, axiom, lemma, corollary. We said that there are direct and indirect proofs. Direct ones are simply you use some start with axioms and then use some rules of inference and come up with the conclusion. These are some examples. Then in the contraposition, we need to change the original statement to this form. The negation of Q implies negation of P, which is the inverse of P implies Q. And then with contradiction, it's a bit different. This time we construct a new statement like this one. P implies negation of Q. But the thing is that this time we need to show that this is wrong. Once you show that this is wrong, then that means the original statement is true. We have some examples. We discussed the square root of 2, whether it's rational or irrational, and we showed that it's an irrational number. We had a quiz, and then we start discussing another type of indirect proof, proof by induction. This is a bit straightforward. For if you want to use proof by induction, then you should have a kind of specific statements, and the statement should be true for some integers greater than some, mostly greater than 1 or 0. And in that proofs, what we do, we simply set the basis. Basis should be actually the first integer in which your statement is true. And in such a case, it's the first positive integer, so that's why we start with n, and n is equal to 1, and show that this is true. After that, we should show that the given, assuming that the given statement is true, we should show that it's also true for n plus 1. Once you show it, then you are done, and you can say that the initial statement, the original statement, is true for all n values. We have some other examples, and this was a kind of a guideline for proof by induction. And sometimes we said that the proof, the statement might be a wrong one, so it's quite impossible to prove that the statement is a wrong one. So what we do, we simply find them contradicting statements. We have gone through an example like this one. The statement is that every positive integer is the sum of squares of 3 integers. And if you start from 0 up to 6, things are fine, but once you check 7, you can easily show that it's not possible to represent 7 with the sum of squares of 3 integers. So which means that you come up with a contradicting, let's say, value, and you can easily say that the initial statement is a wrong one. We cannot prove it since it's a wrong statement. And then later, we focused more on the checkerboards. If you remember, we were playing with the checkerboard, a standard one, having 8 rows and 8 columns. And it's a nice way of showing some different types of proofs. And we started discussing whether we can simply fill in this checkerboard by using simple dominoes, which have just 2 squares. And we said that is easily can be done since we have 64 squares and the dominoes have just 2 squares. So if you divide 64 by 2, then that means you need to have 32 dominoes to tile the complete checkerboard. And then we ask another question: what happens if we remove one corner? This was a bit challenging, but not that challenging. Since once you remove one corner, you can say that there will be 63 squares, and it's not possible to tile it with dominoes having just, as you see, 2 squares. Then we have another example. This time we remove 2 corners, and as you see, in that example, we are removing 2 white squares. So this time, again, the question is the same. Can we tile it by using dominoes? But the answer is no this time, since we did remove 2 white corners, which means that now we have 30, let's say, white squares and 32 red squares. But if you use such a domino, which has a white and a red square, you can easily see that it's not possible to tile the complete checkerboard by using set of dominoes. And then we discuss triominoes, the straight ones. And this is, as you see, a simple straight triomino having 3 squares. And then we have the standard checkerboard. And you can easily say that it's not possible to tile it since we have 64 squares, but you have 3 of them in the standard, let's say, straight triomino. If you simply divide it, then you cannot obtain an integer value, which means that it's not possible to tile the complete standard checkerboard by using straight triominoes. But what about removing one of them? If you remove one corner, and now is it possible to tile this one or not? We said that it's better again we color the checkerboard properly, and once you do that, then you can also use a colored straight triomino and try to count the number of, let's say, gray squares, red squares, white squares, and then if they have the same number, then yes, it's okay. But if you remove a specific corners, then you may not have the same number for all the colors. If that's the case, you can say that it's not possible. But once you come up with a, let's say, a representation having the same number of colors, then it's fine. You can easily tile it. Then let's start discussing a special type of triomino this time. It's L-shaped, not the straight one. And the question is right now, can we tile this complete standard checkerboard having 8 squares in the rows and 8 squares in the vertical, let's say, lines? So do you remember how we approached this problem? We solve it by using the proof by induction methods, the mathematical induction. Or we can also say that recursion, since these are related to each other, we can say that recursive functions can also solve this problem, you're right. But in the proof, what we have done was kind of a proof by induction. Now one corner is removed. We have 63 squares. We have an L shape, and in this L shape trinomial, obviously we have 3 squares, and we don't have a problem with division. If you divide it by 3, that means we will have 21, let's say, trinomials, L-shaped trinomials. So now this is our claim, actually, the claim of our statement. It says that any to the power of k times to the power of k board with one square removed can be tiled using trinomials. So in this case, the value of k is 3, since we have 8 squares in the horizontal and 8 squares in the vertical. So it's an 8 by 8 board, or k is equal to 3. So if you remember the proof by induction, the methods, the steps of proof by induction, we need to state the basis statement. And in the basis, we need to find the first value for k. What is that? It cannot be equal to 0, since if it's a 0, then it's just a simple square. But it should be at least 1. If k is equal to 1, then that means we have a 2 by 2 board. And if you remove the corner of a 2 by 2, let's say checkerboard, then obviously we can easily tile with using a single L-shaped trinomial. Yeah, that's it actually. This is the basis statement. We have an 2 to the power of 1 times 2 to the power of 1 checkerboard. One corner is removed, as you see. The corner is not matter. We can easily tile it by using a single L-shaped trinomial. Now what we do in the induction steps, now we will assume that according to the statement, we can easily tile any 2 to the power of k by 2 to the power of k checkerboard, but the thing is that we need to remove one of the corners. If this is true, then we should show that we can also tile 2 to the power of k plus 1 by the same number. And again, we know that one square from the corner should be removed. So what we do, since we assume that this is fine, this is true, then we simply divide this, actually k plus 1 by k plus 1 checkerboard into 4 smaller checkerboards. And the thing is that we cannot remove this time any square from the smaller boards, since we are looking at the larger checkerboard. We cannot remove any squares from smaller checkerboards. So this is actually the one we start with. We divide it into 4 smaller squares, as you see, so 4 smaller checkerboards. One of them is, one corner is only removed, but the rest 3 smaller checkerboards have all the squares. But the thing is that we can assume that corners from the center of these, actually the larger checkerboard is removed, and we can easily tile a single L-shaped trinomial here into here, so that once we prove that these smaller 3 or 4 actually checkerboards can be tiled with L-shaped trinomials, then it's not a problem for us, since we can also have another extra L-shaped trinomial into that center and conclude that our overall checkerboard, or the initial size checkerboard, can be tiled with L-shaped trinomials. Any questions, guys, about how we do the, let's say, proof by induction for the checkerboards? So if I come here, for instance, this is one of the things actually, and now I will have another one. I have another one here. So now you see, by using for 5 5 L-shaped trinomials in this 4x4 checkerboard. We can easily tile it, and it's also the same for the other. And additionally, I will put another L-shaped triomino. In questions? Okay, when we briefly discussed recursion, and we said that it's highly related to proof by induction or induction methods, and recursion. The main difference in the recursion is that the function, the recursive algorithm or the recursive function should call itself inside. So we can say it like verbally, an example, a verbal example. If you want to understand recursion, then you should first understand recursion itself. So if you write it in a pseudocode, in a kind of an programming language, this is how we do it. And as you see in that function, we are calling the same function again. So we call these type of functions as recursive functions. And the thing is that if you want to solve a problem by using a recursive approach, then you should be able to divide it into smaller instances. But the thing is that once you divide it into smaller instances, you should have similar structures. If you remember the checkerboard case in the L-shaped question, what we have done, we divide the 8x8 checkerboard into 4x4 smaller checkerboards. And we made it similar to the larger one by removing actually corners, and we come up with a conclusion that since the smaller ones can be tiled, then we can also tile the larger ones. As we discuss these, and once you use recursive functions at specific problems, things will be much simpler. And this is another repetition here. If you want to use recursive functions, algorithms in your problem, then you should make sure that your problem can be divided into some smaller tasks. So what we do in the recursive functions, we need to have some base, let's say, statements about the first or second, let's say, values. And then we need to have the recursive definition, and then finally closest function. And we discussed this example, powers of 2. This is the first power, second power, third power. So for our case, base case, we start with s of 1 is equal to 2. But for the larger n values, we can simply have such a recursive definition. This is the recursive definition, the second item here. S of n is equal to 2 times s of n minus 1. So we are always multiplying with the previous s value for n greater than or equal to 2. But for 1, we have this specific base case. Another example is factorial. We have a base case for 0, but for the rest, for n is greater than 0, we can use the recursive definition, n times f of n minus 1. So as you see, is our once you write such a, let's say, definition, you are done with the proof. You don't need to do any more. It's already done by using proof by induction methods. So in also tiling of these checkerboard with L shapes, we have done a kind of an recursive approach. If you consider this smaller checkerboard here, one corner removed, and we can easily tile it with L-shaped triomino. Another example was Fibonacci numbers. If you use a classical approach, then you should have a for loop here. This is how we do it in the classical way. But if you use a recursive approach, then you define the base cases, base statements. These two are the base statements. And this is the recursive definition, and also the closing statement. So we make use of the properties of this programming language. We don't need to have a recursive definition first and then the return function. we have them in a single statement, and as you see, with a shorter number of statements, you can find the Fibonacci number in an easier manner. So this was the point actually we stopped on Tuesday. Any questions, guys, up to this point? Otherwise, I will continue with the binary tree from string. Okay, let's continue with binary tree from string. We will have actually a special part, a special, let's say, section for trees, but this is an important part, let's say, since your first mini project will have some, let's say, assignments regarding the trees and conversion from string to trees. So it's better to discuss it also here in this part of the chapter. And then we will have more time, we will spend more time on different types of trees in the upcoming chapters. So now we have such a definition, and we will have similar ones in the mini project. This is our binary tree. First of all, let me discuss about a binary tree. As the name implies, the binary trees have two children. So you start with a parent, and then you always have at most two children. This is how it proceeds. You cannot have 3 children or more. As you see, sometimes you may have both of them, sometimes you may have right child, left child. It's up to your, let's say, definition, up to your problem. So now we have another definition here. Now this time we have binary trees. So in our example here, if this is T, then this is T1, and this is T2. We simply define it like this by using parentheses, apostrophes, and with the help of it, we can define a kind of a binary tree. And in our definition, in our approach, we will be assuming that nothing else will denote a binary tree. We cannot use another definition than this one. We have another example. Yes, here we go. We have, as you see, many parentheses. We have black parentheses, the most larger one. So this is the T. This is T. And we will have T1 and T2. For simplicity, I didn't use commas, apostrophes, but you can assume that there might be some commas. It's not a big problem. So this is our top tree, top leaf, you can say. This is the top leaf, and then we have the leaves. These are the leaves, or sometimes we call them as actually nodes, top nodes, internal nodes, and the bottom nodes are called as leaves. So as you see, we have a red one and a blue one. These two are the children of the black one, and then we further have the grandchildren of the black one, and they are, this one, the yellow one, is the child of the red one. This is the red one, as you see, and we have another the value of the T1 here, and then we have they're not actually the same color, but this is actually meant to be yellow. So this is the definition of the yellow child, the bottommost leaf of this tree representation. Any questions at this point, guys? I will have another example. No questions? Okay. Yes, now we will be actually assigning some numbers, some values into these nodes, into the nodes of the tree, and also into the leaves of the tree. So right now, if you have a value, kind of a value inside this parentheses, then that means we have a leaf with an integer n. So if I write it as t, oops, I'm sorry. Yes. So this is actually the leaf with a value of n, and this is our binary tree, which has no children at this point. But if you look at the other statement here, then we will have two children, T1 and T2. So you don't need to have arrows, but that's fine. So this is T1, and this is obviously T2. So you may have different representations. For instance, the second one is representing such a case. We have n, but we don't have T1, which means that we don't have left child, but we have right child, which is T2. And for the third one, we have the left child, but not the right child. Again, still they are all binary trees, and as you see, by using such an expression, we can represent these binary trees. And again, we don't have another definition. Nothing else can denote a binary tree. We can only use these definitions. If you have extra commas here, which means that this is empty. So we don't have a left child here. Since in our initial definition, we said that you should have the value for the top node, then you should have the leaves or the children. So once you have an empty case, then that means that part is an empty, we don't have a child here. Or you have T1 and then comma, and you don't have any value after this comma, that means you don't have the right child. So here's another example. Now we have many numbers in this definition. As you see, we have many parentheses, commas. So we will now construct this tree by using the initial expression. Let me write the definition here. This was, if you remember, the definition from previous slide. In our example, n is 5, and then we have this part, which is equal to T1. This is T1 this time, and this blue part is T2. So how we're going to proceed, we will write T1 here, which is left child, and then the right child. But while we are writing T1, again, we will use the same approach. 9 will be the top node of T1, and then we will have some other children. So we will follow the same approach. Now you will see, yes, here we go. We have T1, T2, top node, the top value for T2 is 8, and it's 9 for T1. And the rest is again the same. Now here is a bit complicated, this part. We will have a left children with a value of 2 and a right children with a value of 2, which has 2 more children. As you see, this is the left child of 7, right child of 7, and they are all connected to the ancestor 9. So this is 2 left child, right child, and its children, 4 and 6. And the right hand side, or T2, is much simpler. We have 8 as a top node, and now we will simply have 1 as the left child, and 3 as the right child. And now we are done with the binary tree. This is how we construct the given expression. So by using such an, let's say, a text value, a string, we can represent a binary data structure. This is an important point for your mini project. This is how we construct the binary tree by using a string. So as I mentioned, they are quite useful, and we will make use of this conversion in our projects and try to come up with a CAD model. And we can use these actually expressions, also the string expressions. In the next chapter, you will see that for representing some prefix expressions. And I will go through such a prefix expression. Yes, this is the prefix expression. We have similar values as in the case of previous example, but instead of the values here, now this time we have some operators. There's some prefix expression, which means that we are putting the operators in front of the numbers. That's why it's called as prefix expression. In the next chapter, we will spend more time on prefix, postfix, and infix expressions. Up here, we have a simple prefix expression. And this is representing a mathematical, let's say, expression. And now we will make use of this expression. We will first construct a tree and then do the computation. This is how we do it. Since we have the previous example, we don't need to spend much time. Instead of these node values, we simply write the operators. So now how we are going to calculate the value of this tree? Not that complicated. We should start from the bottommost level. We have 4 and 6 as the children, and the parent says that this is a summation operation. So what we do, we sum these together. What is the value? It should be equal to 10. And then we go one more level. This time our operator is multiplication. We multiply these 2 nodes to children. It will be 20. And also from the right hand side, we should do similar things. This is again a multiplication, 1 and 3. This is 3. So at the topmost level, we have a summation operator. So what are we doing? We are simply summing these two values, and obviously the result is 23. Any questions, guys, about this prefix expression and how we do this computation? No questions? Okay. So how we are going to write these recursive problems, recursive, let's say, algorithms, implementations. As I said in the previous slides, you need to divide your problem into some smaller instances. If you cannot do that, then that means you should find another way and then do your implementation. We should define the base statements for the initial values like 0, 1, maybe 2 sometimes, and then find the smaller problems and try to solve these smaller problems with the same function, the same recursive function. And then later, your implementation should be able to actually combine the solutions of these smaller problems. Since your initial problem is a larger one, at the end of this recursive operation, you need to provide the solution for the larger problem. So it's better, or actually it's a must, you should have a combining part. Yes, this is actually the summary of it. Once you do smaller problems, you pass the results of these smaller problems to larger problems, medium problems maybe, and then to the initial problem. But sometimes, as I said, your problem may not be appropriate for recursive operations, then it's better you find different types of implementation. So what are types of mistake we do once we are doing kind of a recursive implementation? The thing might be about the base case. You may not have a base case, it might be missing or it may not be correct. So base case is an important part, so you should make sure that you have correct base statements. And sometimes you may run your recursive function and it may run maybe days, hours, months, it may not stop. And there might be several problems for termination, no termination. Your problem size may not be decreasing properly, or you may have a stack overflow. You may have problems with the memory, and you should check your data structure, check your statements, and make sure that you don't have kind of problems. Another problem you may have while implementing recursive solutions, you may not be combining the solutions of smaller instances. Since in recursive algorithms, it's an important step. Once you divide your problem into smaller instances, then you should be able to combine the results of these smaller instances. Otherwise, you will have termination problems, you will have some different errors. Another problem you might have is the slow performance of your recursive function. It may be simply due to your poor programming or using some inappropriate, let's say, data structures. So you should do some maybe search and try to find best approach, best types of implementation or some data structures. So this is also important. You shouldn't have any unnecessary computations. You shouldn't recomplete the same value once again, since we are trying to decrease the time spent on the computation by using the recursive function, recursive implementation. So you shouldn't be doing any recomputation.